Today we're going to see a very important design of control systems principle and method called the root locus method, discovered by Professor Evans back in the 1940s. And the idea here is, if you have the block diagram as you see on the screen here, you see you have this. This is your plant, right? This is your plant in here. We have a single unit feedback, just feedback the output, and this is your reference point. And the only thing that we are going to change is this constant in here. Now you know that this this plant could be a transfer function that has different roots, and could be a transfer function that has different poles. You also know that the transfer function, the poles and the zeros are going to determine how the response is. Okay, so let me just get this changed to okay, there we go. What I was trying to say is, if you begin plotting the let's just do it here. If this is the complex plane and you have roots here on the real axis, the response is going to be like this, right? If you have them here, let's say, the response is going to be like this, yeah? And if you have them on this side like this, you know this is going to be a little disaster to have them on the right hand side, because the system will start like this and then it will blow up. Yeah. Same thing if we do the drawing over here of the response, it will start like this and then go will blow up. And in here basically the system is, they oscillate a lot, right? See? Very good. So knowing this, you see what Evans is saying is, if we change this constant, what we are changing is the transfer function. But you see, if originally this plant has the let's do it over here. Let's say that for the sake of example, the original poles are here. And if you change the value of k, let's say they become here. Right? And if you keep changing it, they might be here. And then all of a sudden, you see, there is a point where this tendency will cross the real axis into the dangerous zone over here. See? And this is what Professor Evans is saying, is that if we give values for k and then we plot the lossy of the points like this, as you know, the poles of the transfer function, they are called the roots, right? Poles. So these are also the roots of the characteristic equation, right, of the system, the denominator of the transfer function. So if what he is saying is, with the change of the value of k, you change the position of the poles. And therefore, at some point, if you cross the, let's say this is real and this is the imaginary axis. If you cross the imaginary axis, you have crossed the stable and unstable region, right? Two into the unstable region. So what he was saying is you could predict when the system would go unstable by changing the value of k. So k is going to go from 1, let's see, to infinity, right? Like this. This is going to be the change of k. So the basic concept of the root locus is, can we plot the changes of the position of the poles as a function of the change of the value of k? Very simple concept, all right? So we'll see some more variations of this. You could see here that if you have this transfer function like this, you have the see, the transfer function is 1 over s plus a. So you're going to have that the characteristic equation s times s plus a equal to 0, right? Consequently, s is equal to 0, but also s is equal to minus a. Yeah? So you're going to have a transfer function that produces this kind of locus here. So you study what, as a function of k, what it would do. So I propose that we enter this transfer function into MATLAB and see what happens. We are going to ask MATLAB to change the values of k from 1 to infinity and give us where those poles go. Okay? So why don't we do that? So let's just go ahead and we're going to say keep here, and then let's just go to MATLAB right here. All right, and let's enter a transfer function like the one we had in the on the diagram there. Okay, so I have shown you there's a couple of ways to enter the transfer function. I am going to enter the transfer function. I'll just do it the same way as in the fraction form, like you define the variable s is of the transfer function of the type is like this, and then you say, okay, the transfer function g is going to be equal to what do we say, 1 divided by parentheses, this would be s, multiply by s, what do we say, s plus, let's say 5. How is that? Like that. See? And if you do that, you have this transfer function. Okay? What we're going to do is we are going to ask the computer, it says, plot for me the location of these poles by plotting the root locus of all these roots. G is my transfer function, and the values as a function of change of k. So here's what that is saying. It's saying that you see you have a root at the 0 here, and the other one is at minus 5. And if you change the value of k, what's happening is You see, I hope, okay, okay. I I hope you see here. See, the MATLAB is pretty nice in this regard, but you need to understand this is the imaginary axis right here. This is the real axis, so this is the 0, right? Okay, this is -5 in here. See, you could actually touch anywhere on the screen, and it'll tell you the value of the. Uh, see, right here it was on that point, and this is so at k is equal to 0 or 1, let's say you have k is equal to 1, you have the transfer function there. So as you go along, you see again, see over here 1.85, and you go like this. If you keep keep track of the plot, the blue one goes like this and then goes up, and the green one starts over here as k is going up. Okay, see, and it goes like this and then goes this way. So that's why this is blue, the other one is green. What I'm going to do is let me try this and see if this would allow me to actually write on it. Okay, let me show this. What I was trying to say is it starts over here, right? And then the blue one is going this way. And then as k goes up, goes this way. Would this system ever be unstable? See, the green one goes this way and then goes this way. Would the system ever be unstable? The way it looks based on this root locus method, the system would never be unstable, because it doesn't matter how big the transfer function, how big k gets, the location of the poles keep going like this, see? And of course this way. And they will never get to this. This is the axis here. This is your imaginary axis here. And this is your real axis. See? Huh? So what Evans did, it was a wonderful contribution to the field, because he could predict what the system is going to do with the value of k. If you look at it from the basic control systems idea, this is like putting proportional control, right, to this transfer function, and changing the value of that control and realizing that the system will not go unstable. But that's not the case with others, though. With others, the system would go unstable. And that is the idea that we have in here on this presentation, that we can look at different types of controls, different types of situation of the transfer function here. See, for example, if you have this like this, here it shows very clearly the roots would go in and then they would break away. And in here, this would never go unstable. All right? But there could be other situations where you see the roots, they do all kinds of things. In this one, for example, for this particular transfer function, they would go like this, and it would go parallel to a line called the asymptote here. Or you'll have a situation where they would never go on the other side. But there are others that would do that. Now, in the past, and many textbooks teach you techniques to draw this root locus by hand. I don't advise that at this point. We have MATLAB. You have seen how we can do it, and that would be the best thing to do. Here we have another type of transfer function, and this kind of root locus. So why don't we give it a try, for example, to this form, and see how we do this. Okay, let's go to our MATLAB. See, remember the transfer. Remember this this kind of transfer function in here. I'm going to go to MATLAB and then build this. Okay, so let's say that we have a. I'm going to call it G2. Yeah, the different transfer function. This is going to be a 1, and then I'm going to go ahead and do parentheses with no, divided by parentheses s multiplied by I'm just going to put it exactly in the form that is in there. Okay, so this is going to be parentheses. Let's give it a tau, let's say a 3, and then times s, and then we say plus 1, close parentheses, then multiplied, open parentheses, let's say 5 multiplied by s plus 1, like this. How is that? Am I correct? So we have 1 over s times 3s plus 1 times 5 s plus 1, and then we do this, and we have the correct transfer function in here. And what we are going to do this time is, let's get rid of the first plot that we had, and now we are going to say arc locus of the transfer function G2, like that. And let's see where that leads us. Wonderful. Do you see? This is a wonderful test for this concept, because you see here, when the transfer function, I'm going to let me see if I can get this so that I can actually um, um, put some comments on it. Okay, here we have the transfer function. Let's follow. It's got 3 roots, right? One at 0. As k goes up, goes this way, and this one goes like that. Yeah, this other one starts like this at some point, and then it goes this way. So this transfer function, for sure, in some value of k, it will go unstable. This root will go this way. So you see, what Evans' root locus method gives us is the ability to track down where the poles go as the change of k, and to determine where the system would go unstable. Now, to make that test, what I would do is, you see, you have the ability to click. If you click here, see where it says gain 0? Let's follow the green one, right? Gain 0.21, and then gain over here. See here, gain 0.2, and there is your system already unstable. And the computer is telling you what the value of the gain is at a particular location. So you could actually find it, see? This is a MATLAB, when you do the root locus, is very nice. I think you could find out exactly when the system will go unstable. Okay, that's the concept of the root locus method.